Good evening children and welcome to online teaching session, and today I am going to cover these topics. First topic is ionization constant of weak acid. Ionization constant of weak acid. That means Ka is ionization constant. Now imagine a weak acid of type HX or Ha. Here the thing is proton should be there in it. That's it. And this weak acid, to this weak acid, water is added, H2O. Right? And this is weak acid. Right? When these two react with each other, here this is weak acid. Acid means one which is going to donate proton. So this will donate proton to water. So we'll get hydronium ion in aqueous medium, and then H minus ion in aqueous medium. Right? This can be CH3COOH. In that COOH, H is there, no? That part is this. And X can be CH3CO, ethanoic acid. That way it can be taken. And this is reversible reaction. Right? Now, what I am going to do in this reaction is, I will write first how much amount of the main reactant is taken when the reaction is not started. Right? How much amount of that weak acid is taken, that much will be there. Means when time, see I have taken 1 mole of HX, weak acid. When time t is equal to 0 seconds, then quantity of this weak acid is 1 mole. Means reaction is not started. Then quantity of hydronium ion formed is 0 mole. Right? Quantity of X minus 0 mole per liter. In that way. Okay. Now, what I am going to do is, I will begin the reaction. Means to this 1 mole of weak acid, I will add little water. Then the reaction will begin. On the other hand, hydronium ion and X minus ions are formed. When the reaction begins between these two, that means when time t is equal to, right? So here t is equal to 0 seconds. Let me write in this way so that it will be very clear. Time is equal to 0 seconds. Let it be in that way, it will be more clear. 1 mole of HX, weak acid, will be there as it is in that quantity. And when time t is equal to, when time is equal to t seconds, let me write in that. Then alpha amount of weak acid undergoes ionization. Alpha amount or alpha degree of, degree means amount or quantity. So alpha quantity of this weak acid will undergo ionization out of 1 mole. So how much amount of weak acid will be left out means we write 1 minus alpha. So here degree of ionization is alpha. Means that much amount of weak acid is ionizing. So same amount of hydronium ion will appear. Same amount of this negatively charged ion will also appear on the other hand. So here alpha amount of weak acid undergoes ionization. Right? When time is equal to t seconds. Now, in terms of concentration, when we are asked in terms of concentration, when we are required to write, then what we will do is whatever amount of weak acid, hydronium ion and negatively charged ions are there, they are multiplied by C. C for concentration. So here I write C into 1 minus alpha, and here C into alpha, and below this again C into alpha. Right? Now I will apply law of chemical equilibrium. So when law of chemical equilibrium is applied, we get Ka is equal to molar concentrations, products of molar concentrations of these reactants, means C alpha into C alpha divided by molar concentration of weak acid, that is C into 1 minus alpha. Here Ka stands for, it was taught in the previous session, that Ka stands for dissociation or ionization constant of acid. Now this is equal to, here C gets cancelled, right? So you will get C alpha square divided by 1 minus alpha. So here we have 3 variables, 1, 2, 3. Out of these 3 variables, if you know any 2 variables, the third unknown one can be calculated. And remember, here unit of concentration is mole per liter. Right? So unit of concentration is equal to mole per liter. That is nothing but capital M. Right? So that's about ionization constant of weak acid. Okay, now we will move to solubility constant. Solubility constant. Number 2. Solubility constant, and it is symbolically represented by Ksp. It is a constant, right? This property, solubility constant, solubility product, solubility product, Ksp is a constant, and this property is exhibited by the sparingly soluble salts. Salts are of 3 types: completely miscible, sparingly miscible or sparingly soluble, and insoluble or immiscible salts. And this property is exhibited by sparingly soluble salts. like barium sulfate, silver nitrate, etc. Now, if I add water to barium sulfate, it's a white colored precipitate. Right? If we add water to this barium sulfate, white colored crystalline substance, it dissolves in water to form aqueous barium sulfate, and that undergoes ionization to form barium dipositive ions in aqueous medium and sulfate dinegative ions in aqueous medium, and it is a reversible reaction because it is sparingly soluble. Now, if we apply law of chemical equilibrium to this equation, then Ksp is equal to molar concentration of barium dipositive ion multiplied by molar concentration of sulfate dinegative ion divided by molar concentration of barium sulfate. Right? This expression we will get. And in the case of this equation, let me write again. Barium sulfate in aqueous form undergoes ionization to form barium dipositive ion in aqueous form and sulfate dinegative ion in aqueous form. And Ksp of barium sulfate is equal to, here, how is it calculated? Let us see. And this is equal to 1 into 10 raised to minus 10. Here, how much amount of barium sulfate dissolves in water? Right? How much amount of barium sulfate is soluble in water? That much amount of barium and sulfate ions will be appearing. So, solubility of barium dipositive ion, say S. Solubility of sulfate dinegative ion, say S. Right? Now, Ksp is equal to barium sulfate is equal to S square. That means 1 into 10 raised to minus 10 is equal to S square. Or S is equal to square root of 1 into 10 raised to minus 10. This is equal to 1.05 into 10 raised to 5. Right? This value we will get. So in the numerical, this Ksp and S square, they are correlated. So these two are variables. Out of these two variables, if we know any one, the third unknown one can be calculated. Yes, children. Now we will move to common ion effect. This phenomenon is used when high degree of purity is expected in the case of compounds. Now let me give one example for this, that is brine, not brain, brine, which contains sodium chloride, sodium sulfate, magnesium sulfate, right? Calcium chloride, calcium sulfate, magnesium chloride, etc. salts. And usually seawater contains brine. In that brine, we have all these salts. And the important salt which is required for us here is sodium chloride. Seawater is not potable water. Right? We cannot drink that water. Number 2, sodium chloride in pure form is very much required for us. So what are not required for us are these salts. So these are all impurities. So these impurities should be removed. When all these impurities are removed, we will get pure sodium chloride. For this purpose, this common ion effect phenomenon is used. Right? So big industries are using this phenomenon to make pure sodium chloride salt, which is fit for our consumption. And to that sodium chloride, calculated amount of iodine is added because it has medicinal value. Then that salt will become iodized salt, and then that is sold in the market. Fine. Now we are going to see how this pure sodium chloride is obtained. When sodium chloride, see, as I told you, it is there in seawater. Means you have to write here aqueous. Right? When this sodium chloride undergoes ionization, it forms sodium ions in aqueous form, and then chloride ions in aqueous form. Right? When sodium chloride undergoes ionization. Our focus is on sodium chloride. That's why I have written here sodium chloride. Then next, what I am going to do is hydrogen chloride. I will pass this hydrogen chloride right into this sodium chloride solution. Here hydrogen chloride will also undergo ionization to form H plus ions and Cl minus ions. Here when sodium chloride is undergoing ionization to form the ions, that time the reaction will not occur in opposite direction. Right? It is not reversible in nature. When HCl alone is undergoing ionization, that time also HCl will not be exhibiting. Means the ions formed from it are not going to exhibit backward reaction. Now if you observe these two equations, you can see common ions in both the cases. That is chloride and chloride ions. Product side concentration of chloride ions have become more. Now you recall Le-Chatelier's principle. According to that principle, whenever concentration of any substance is high on any side of the equation, LHS or RHS, then the reaction will take place in that direction where the increased effect of concentration of the substances get nullified or balanced. So according to Le-Chatelier's principle, same principle we can apply here, right? So Le-Chatelier's principle we are applying. So when this Le-Chatelier principle is applied, according to that principle, concentration towards RHS has become more. So the reaction will take place in opposite direction to form pure sodium chloride. 100% pure means high degree of purity is expected because of common ion effect. Because of that reason, we will get highly pure sodium chloride salt. Right? That is taken and it is pulverized, means converted into powder in small crystals. And to the calculated amount of sodium chloride salt, particular amount of iodine compound is added. Then that sodium chloride is said to be iodized salt. And then it is filled in the pockets. They are sealed and marketed. That's about common ion effect. Okay. Now we'll move to polybasic acids. Polybasic acids. These polybasic acids are also known as polyprotic acids. Poly means many, right? Protic refers to protons, means those acids which contain many protons in them, and in turn they are able to donate those protons. That is the meaning. Once again, the concept of polybasic acids or polyprotic acids. Those acids which contain many protons in them. Many means here more than one. It can be one proton or two protons or three protons. And in turn, they should be able to donate those protons. Right? Then they are said to be polyprotic acids or polybasic acids. We have polyacidic bases also, but this session 30% syllabus is decreased. In that topic has gone. So that is not there. So you please focus on this concept. Okay. Once again, polyprotic acids are nothing but those acids which contain more than one proton in them and are able to donate them. Right? According to one of the theories, acid is a substance which acts as proton donor. So here polyprotic acid means it has to donate more than one proton. That is the meaning. Okay. Now let us see examples for this. First example is H2X. This is what given in the book. X means it can be SO4. Then it will become H2SO4. Right? So this is what given in the book, but what I will do is I will take specifically acid which is able to donate proton, right, instead of H2X. So we can take here H2X, right? If X is equal to sulfate anion, then this H2X will be like this, H2SO4. Right? This H2SO4 I am writing this way. HSO4. This is diprotic acid. This is called diprotic acid because this is able to donate two protons. Right? How it is going to donate? Let us see. When this dihydrogen sulfide, that is chemical name of sulfuric acid, when breaking of the bond takes place here, then we will get HSO4 ion, that is bisulfate ion or hydrogen sulfate ion plus proton. In next step, so formed bisulfate ion, HSO4 minus ion, right? So bond will be here in between hydrogen and the sulfate. Again, if this bond is broken, right, then it becomes sulfate dinegative ion in aqueous medium and the second proton. in aqueous medium. Now, in this case, if we apply law of chemical equilibrium to these equations separately, right? So let this be equation number 1 and this is equation number 2. So when law of chemical equilibrium is applied to equation 1, applied to equation 1, we get equilibrium constant of acid, A for acid. This is equal to product of molar concentrations of hydrogen sulfate ion multiplied by proton divided by molar concentration of sulfuric acid. Yeah. Next, if we apply same law of chemical equilibrium to equation 2 and 2 respectively, we get, in the case of equation number 2, Ka is equal to, again, product of molar concentrations of sulfate dinegative ion multiplied by molar concentration of proton divided by molar concentration of bisulfate ion. This expression will be. Here two terms we have got, that is ionization constant Ka. In order to distinguish one from the other, we will write Ka1, Ka2. Ka1 stands for ionization constant of sulfuric acid when it has donated one proton. Ka2 stands for ionization constant of bisulfate ion which has donated proton present in it. So Ka1 and Ka2 stands for ionization constants of sulfuric acid and bisulfate ion respectively. Yes children, now let us see the last topic of this chapter, and that is last topic in this session, right? And that is buffer solution. What is meant by buffer solution? What are the different types of buffer solutions and how they are prepared? And that is fifth one, buffer solution. See, our blood, our urine, both have specific pH values. Always they are constant. If pH value of the fluid, like blood, if it is changed, pH value of our urine, if it is changed, then that shows malfunctioning of our body. Right? So, blood and urine have specific pH values. Right? Variation in these pH values will indicate malfunctioning of our body. Next, buffer solution. Let us see the concept. Buffer solution means a solution which is capable of opposing the change in pH when small amount of acid or base is added. This is the concept. So, a solution which opposes change in pH when small amount of acid or base is added. I'll give you one example. Imagine you have taken potable water in a glass, right? Water which we are drinking every day doesn't have any taste. If we add a solution which has sour taste, means the juice of a sour fruit, if we add, then that potable water will become sour in taste. Before adding that juice, pH of that water is 7 because water is neutral substance. When that juice is added, it becomes sour, means its pH becomes less than 7. Means that solution's pH is changed when that acidic substance is added, that sour juice is added. Number 2. Again, you have taken potable water in a glass and its pH is 7 because it is neutral. Now, a small amount of soap solution is added to it. Right? If we taste, nothing will happen. If we taste, it gives bitter taste. Means its pH is hiked from 7 to 9 or 10 depending on how much amount of soap solution or detergent powder is added. So here what I want to tell you is, as long as acid or base is not added, that solution remains neutral and its pH is equal to 7. Right? If we add any acid or base in small quantity, immediately its pH fluctuates, changes. Therefore, to prevent this, we need to make buffer solution. So, next is preparation of buffer solution. In this we have two types, acidic buffer solution and alkaline buffer solution. So, accordingly we will see one by one. First one is preparation of acidic buffer solution. Whenever we want to make acidic buffer solution, we need to take weak acid and next salt. Right? So this consists of mainly weak acid plus salt of weak acid. Right? Now we will take specifically one weak acid and one salt of the same acid, that is CH3COOH. This is weak acid. Right? In aqueous medium, AQ stands for aqueous medium. It undergoes ionization to form ethanoate ion plus H plus ion. Weak acid over. Now we will move to the salt of that weak acid. And salt of that weak acid is CH3COONA. This is salt of weak acid. Its name is sodium ethanoate. Right? In aqueous medium, this salt undergoes ionization, thereby to form ethanoate ion and sodium cation. Right? Now, in these two equations, you can see the common ions, as you had seen in common ion effect phenomenon. Here, common ions are these two. Ethanoate ions. These are common ions. Right? Means concentration of products towards RHS in mode. Now, if I add what you call any acidic substance in small quantity, that acidic substance will donate proton that will react with ethanoate and the reaction will occur in backward direction, thereby to form ethanoic acid, thereby to maintain the same pH. Hope this is clear to you. And here we have applied what you call Le Chatelier's principle. According to Le Chatelier's principle, the reaction will occur in backward direction. Now, if we apply law of chemical equilibrium, when law of chemical equilibrium is applied, right? This is acidic buffer solution. So when law of chemical equilibrium is applied here, we get, right, Ka, that is ionization constant of acid, is equal to molar concentration of ethanoate ion multiplied by molar concentration of proton divided by molar concentration of ethanoic acid will get. Right, let this be equation number 1. Now what I am going to do is, I will go for rearranging this equation by taking molar concentration of proton towards left hand side. This is equal to, now the expression will become Ka into molar concentration of ethanoic acid divided by molar concentration of ethanoate. Right? This is equation number 1 only. Just I have taken a different form of it by rearranging. Next, same equation I am going to write in this way. H plus ion molar concentration is equal to ionization constant of acid Ka into here ethanoic acid, CH3COOH is acid. So I will write acid in this way, molar concentration of acid. That means it is applicable to any weak acid, that is the meaning. Divided by molar concentration of ethanoate ion. Ethanoate ion has come from sodium ethanoate, means salt. So I will write here salt. Right? Let this be equation number 2. Now what I am going to do is, I will take minus log of H plus ion and also the other part which is lying towards the right hand side. So when minus log is taken on either sides of equation 2, we get H plus into minus log. So minus of log of H plus ion molar concentration is equal to minus of log of Ka into minus of log of Ka minus molar log of molar concentration of acid divided by molar concentration of salt. Right. This equation, in this equation particularly, let this be equation number 3. Minus of log of H plus or negative logarithm of H plus ion concentration is equal to pH. And minus of log of Ka is equal to pKa. This was taught in previous session, in the previous class. Right. Minus log of molar concentration of acid divided by molar concentration of salt. Right? Let this be equation number 4. Now, in the case of particularly ethanoic acid, if we take pKa value is equal to 4.75. So here pH is equal to that value you can put here in place of pKa 4.75. So if we want, this minus sign can become plus if we take molar concentration of salt and acid upside down. Molar concentration of salt divided by molar concentration of acid. And here pKa value we can write as 4.75. And this equation is known as Hasselbalch equation. Hasselbalch equation or Henderson-Hasselbalch equation. This equation is called as. This is in the case of acidic buffer solution. That's how it is prepared, and the popular equation, that is Henderson-Hasselbalch equation. In this 1, 2, 3, pKa value is constant out of these three variables. If we know any two variables like pH or molar concentration of salt and the acid, out of these, if we know any two, the third unknown one can be calculated. Now we move to alkaline buffer solution. How is it prepared? Preparation of buffer solution. In this second one, that is preparation of alkaline buffer solution. And always alkaline buffer solution is prepared by taking the weak base and its salt. Here weak base and the salt of weak base we require. And weak base is ammonia solution or ammonium hydroxide. Right. In aqueous form, it undergoes ionization to form ammonium cation and hydroxyl anion. Now, if we take its salt, that is ammonium chloride in aqueous form. Okay, it undergoes ionization thereby to form ammonium cation and chloride anion. Right. Now, we are going to apply law of chemical equilibrium to this. And before that, let us see the common ions, ammonium and ammonium cations towards right hand side. Right? Concentration of these products are more. Now, if we add any base, that will donate OH minus ion, and that OH minus ion will combine with ammonium cation, thereby to form NH4OH. Means pH is maintained constant. That is the point. Yes, children. Now we are going to apply law of chemical equilibrium. When law of chemical equilibrium is obtained, then Kb is equal to molar concentration of NH4 plus ion multiplied by OH minus ion divided by molar concentration of NH4OH. Right? Now what I am going to do is I will take OH towards left hand side. Let this be equation number 1. And when OH minus is taken towards left hand side, then equation will become Kb into molar concentration of ammonium hydroxide divided by molar concentration of ammonium cation multiplied by OH minus anion. Right? Next, here OH minus I write as it is, and Kb, that is dissociation constant of base, I write as it is, and here NH4OH is base. So what I will do is I write here base molar concentration. That means it can be any weak base divided by here OH minus I will take it towards Kb into NH4 plus divided by NH4 OH is taken and Kb into NH4 OH should not be there. NH4 OH and here NH4, yeah. And in this case, and in place of NH4OH, I will write base. In place of ammonium cation that has come from ammonium chloride, so there I will write salt. So the equation will be generalized. It can be applicable to any base. So I will write Kb, and in place of NH4OH I will write base, and in place of NH4 plus I will write salt. Right, let this be equation number 2. Next, when negative log, minus of log is applied on either sides of equation 2, we get minus of log of hydroxyl ions molar concentration is equal to Kb is equal to minus of log of Kb, that is ionization constant of base, minus of log of molar concentration of base divided by molar concentration of its salt. So let this be equation number 3. Negative log of OH minus ion is nothing but POH. Like pH, this is POH. Now this is equal to negative log of Kb is equal to PKb minus of log, and here this minus sign, if we want to write or if we want to make it plus, we can make it, but molar concentration of salt and base should be written upside down, means in this way, log of molar concentration of salt divided by log of molar concentration of base. It can be written in this way. Let this be equation number 4. And pK value in the case of most of the alkaline buffer solutions is equal to 9.25. If we want, we can substitute in place of pKb. Then POH, molar concentration of salt, and molar concentration of base, means 3 variables. We can see clearly in equation number 4. Out of these 3 variables, if we know any 2 variables, the third unknown one can be calculated. So that's how alkaline buffer solution is prepared. Thank you, children.